synchrotron light to perform photoemission experiments. And so the idea to have an experimental talk here in this theoretical school is to remind you, first of all, that physics is an experimental science. So, of course, we like to study the theory, but we need to start from experiments. And then Polina will give us the experimental view on the bus structure and the properties of materials. So it's important to keep that in mind.
Okay, perfect. Okay. How to use the pointer? Sorry.
The pointer?
Sorry.
My bad. Allora, con questo fai il pointer.
Ok.
Questo sopra, avanti e indietro.
Ok. Avanti e indietro. E pointer. Okay. Good morning, everyone. I would like to thank the organizer for inviting me and for giving me the possibility to make this talk. I am an experimentalist, so my idea is to give you a broad idea what is the experimental photoemission spectroscopy. I will introduce the photoemission spectroscopy from an experimentalist point of view, give you some details, not too much details of the photoemission experiments, some examples of the angular solid photoemission of simple two-dimensional electronic bands, and we talk about the potentiality. Potentiality of ARPES, yeah, okay. I can take out the mask. So, ARPES, the photoemission, as you know, probably is based on the photoelectric effect when the light with sufficient energy is illuminating the sample surface.
Sorry, Polina, I think we have an issue because on Zoom we are not looking at the slides, so I have to check with the guy. Because we are just seeing the video, but not the slides. I think we're, yeah, okay. Thank you. Okay, so now we also see the slides. Thank you. Sorry.
Yeah, yes. Okay, so yeah, when the bulk sample is illuminated with some light with sufficient energy, it can leave the electrons. So this effect has been discovered in 1886 for the first time. It was explained by Albert Einstein in 1905. So the kinetic energy of the emitted electrons does not depend on the intensity of the light. It depends only on the photon energy of the beam and on some parameters, for example, also the work function, that is the potential that the electrons need to overcome while leaving the surface. So here is the simple relation between the electronic structure inside the solid and the outside of the solid of the photoemission spectrum. So it's just the energy scale is just simply translated from the binding energy to the kinetic energy by using this relation. So we can see also that there is a sudden drop of the intensity above the Fermi level of the maximal energy that can, maximal kinetic energy that the electrons can have. So, and just below the Fermi level, we can see this complex structure. This is derived from the valence band electrons that are weakly bounded. Then deeper in the energy, we can see the core levels, which are, have easier shapes somehow. And there is also a exponentially growing background that can, that is derived from the inelastically scattered electrons. And also the information of this background can also be used for analyzing the electronic properties of the materials. For example, it can be used to determine the work function of the element. The core levels are typically used to analyze the chemical composition of the materials, also its atomic composition, stoichiometry, and so on. And one of the important parts is also the electronic structure, electron band structure, which is close to the Fermi level, which is given by the valence band electrons. So the main scope of the photoemission analysis is to reconstruct the behavior of the electron inside the sample from its photoemission spectrum. So the typical photoemission setup just need these three elements. That is a photon source, That can be, for example, a ultraviolet lamp, it can be X-ray tube, it can be synchrotron, it can be laser, free electron laser, and so on. It needs a sample that will be illuminated by light, and it needs an electron analyzer. That the most common usually electron analyzers are the hemispherical analyzers, and then there are some more exotic types of analyzers like momentum microscope, type of light microscope, and so on. And the sample for the photoemission need to be ordered solid, like might be bulk material, might be thin film, might be multi-layer or molecular rail, and so on. So these are typical photon sources that are used for the photoemission. The first two, the gas discharge lamps and X-ray tubes, these are commonly used in the laboratories, in the laboratory photoemission. They are, they have relatively low cost. They are more available than the rest, and but they have, say, somehow lower resolution. Typically, the resolution much lower, and they have large spot size. And then there is also, they also have fixed photon energy. For studying the valence band, one normally use the gas discharge lamps that provide these typical to photon energies, and then also the X-ray tubes are commonly used to study the core levels. Then the synchrotron lights, which is, say, the one of the commonly used techniques to study the electronic structure. It provides a continuously tunable light within a very broad range of the energy. It has also high intensity brilliance. It has variable polarization and can also have smaller spot size and many other advantages. Then there are also laser sources to provide the light on the sample, and they typically have a limited range of energies. But their advantage is that they can permit the time result studies, and they also have much higher energy resolution. And there are also some exotic, more exotic things which are more hard to access, as a free electron laser. This is a typical example of a photoemission beamline. This is all this is needed just to bring the light on the sample and to study the photoemission. So for the photoemission beamline, you typically need a synchrotron. You need all these optics like undulator. You need this mirror. You need a monochromator in order to produce a monochromated light and to achieve a very high energy resolution, and all these mirrors and so on. So synchrotron light-based photoemission so far is considered one of the most powerful tools in studying the band structure of the elements and the photoemission. But the disadvantage of this technique is that you typically need a synchrotron. And so to access an experimental synchrotron, one needs to write an experimental proposal, which is a sort of project. And these projects need to be approved in proposal committee. So typically, to perform an experiment at synchrotron, you need from 3 to 12 months from the time you decide to do an experiment, in case your proposal is successful. Typically, the photoemission is made in this range of energies that is from 10 to 1000 electron volt. It's so-called surface sensitive regime. So if we look on the inelastic mean free path of the outcoming electrons, that means the maximum inelastic mean free path is not more than 2 nanometers. That means that compared to the typical thickness of monatomic layers of elementary materials, means at maximum you will probe 10 layers in the surface. Like if you use 5 to 100 electron volt, it would be even smaller. So we'll probe 1 to 2 monatomic layers, and this particularity asks for a very clean surfaces, and also it asks for ultra high vacuum conditions in a way that your sample surface can be measured without being destroyed within several hours. So, and also for photoemission, the samples need to be conductive. So the samples might be, for the photoemission, can be either prepared ex situ, like bulk crystals, like several topological materials. They can be prepared outside. They can be brought in the experimental station. They can be cleaved in order to get the clean surface. They can be exfoliated like graphene samples. Either they can also be prepared in situ, or the same topological insulators might be grown by in bee growth. The graphene can be preparated also in situ by dosing some gas, by chemical vapor deposition, and so on. And also the clean surfaces can be prepared by sputtering annealing techniques. So this is typical layout of experimental setup for studying the photoemission. So you need a place from where you insert the samples. Then you need all these experimental facilities to prepare the samples, to dose the gases, to sputter, to anneal, to cool, to heat up the samples, and also for making some basic checks of the sample surface. And then you can finally, when you think your sample is ready, you can transfer it in front of the beam. And you can take your photoemission normally with the analyzer. So, and this is how in reality all this stuff looks like. So this big piece is the hemispherical analyzer that measures the photoemission spectra. These are the experimental chambers. These are all the facilities to prepare, like gas bottles and so on. These are manipulators in order that you can transfer the samples here and there and prepare them. And there is also all these big features that are destined to create and maintain the UHV condition, the ultra-high vacuum condition, so that the sample surface may remain clean. So what is the typical how does the typical photoemission spectrum look like? For example, if I talk about the XPS or ASK, when we use somehow, normally people talk about XPS, they are talking about somehow high energies, high photon energies, but XPS spectrum can be also taken in surface sensitive regime, and you can take it also even with helium lamp, you can take the XPS spectrum. So normally in this type of experiment, you are not interested in the angle distribution of electrons. You are typically taking the intensity of the emitted electrons as a function of their kinetic or binding energy. So the conversion of this type of spectra is very easy. You just scale the kinetic energy into the binding energy, and that's all. So this is a typical spectrum that is taken on topological insulator, tin bismuth telluride. And these are these sharp peaks are the core levels from which we can understand the sample composition. Also, we can analyze the ratio between the peaks, and so we can check the sample composition whether there's it has the correct stoichiometry. And close to the Fermi level, we can see the valence states, which in this particular case are very, very weak with respect to the core levels. And this XPS analysis can also provide many useful information on the samples. For example, this is the study on the molybdenum carbide MAXEN. And it has, so this study shows two peaks that are related for the molybdenum and carbon, which are intrinsically, the elements of which the MAXEN is built. And we can estimate from these two cores, we can estimate the ratio between the two elements. We can say whether there is some excess of carbon and say that the material synthesis was correct or not correct. We can also see some adsorbites which are on top of the materials. Normally, these core levels are fitted with different procedures in order to find different components in the spectrum. From these components, from the binding energy of the components, you can understand something about the type of the chemical state of these elements. And finally, you can just also, without information about the angular distribution of the electrons, you can also see the valence band, and just from the shape of the valence band, you can say whether the material is isolating or it is metallic. Okay, and when one talks of the valence band, normally the people study the valence band with angular resolved photoemission. That means that also the emission angles of the electron is taken into account. So basically for this reason, either one can use a single channel analyzer that can just analyze one emission angle of the electron, and then you can rotate the analyzer. But the result is always the same as the intensity of the emitted electron versus kinetic energy. Either in the modern analyzers, you can take in parallel several angles on the detector. You can take like several hundred of channels at the same time. You always save the same spectra. You will have some 600 spectra at the same time. And conventionally, these spectra are shown like image plots, where the brighter color corresponds to higher intensity and the darker color corresponds to lower intensity in this particular plot, but there are also some very exotic color scales that are used in ARPES. So then this, one need also to link the information about this spectra that is measured to the bands inside the structure. For what regarding the two-dimensional bands and the simple system, the relation is rather easy because the parallel momentum of the electron that is parallel to the surface is conserved. So it can be directly converted from the angle using this formula. And the binding energy of the electrons can be also get from its kinetic energy using these simple relations. They can be simply related to the Fermi level if the sample is metallic. And what is particular also of this type of conversion, that the spanned range of the angular of the wave vector depends strongly also on the photon energy. So the lower photon energy you use, the smaller information you will get. And it can also be the field of view can also be widened, but in the case you have to take several spectra, rotating the sample, and so on. And then, in case one wants to study the anisotropy of the sample, one can take the Fermi surface mapping of the sample. Either he can rotate the sample in front of the analyzer, or he can just, like here, tilt the sample in front of the analyzer. Also, in some modern analyzers, this procedure can be done from the analyzer optics. And then one can get a three-dimensional set of data. From there, one can build, one can cut and get, for example, the Fermi surface. If he cut this cube at the Fermi level, are there some constant energy cuts, and he can understand something more about the band's anisotropy. So the band structure, in the case of simple two-dimensional systems, can also be very easily compared to the LDI DFT calculations. For example, here I show an example of silver thin films and its electronic band structure, which is analog of the particle in a box picture. So we can see this number of quantized states, which are quantum well states in thin films that are due to the electron confinement in thin film. And we can see that ARPES can very nicely show very similar parabolic-like states, which was formed also is very similar to what DFT calculations predict. Next, there is some example which we did. These are example on quantum well stage which were observed on iridium or on ytterbium thin films. So we can see that for sufficiently thick films, we can observe a number of states that cross the Fermi level, and this number of states increase with the film thickness, from where we can deduce that all these states are coming indeed from some bulk state, which is supposed to cross the Fermi level. But initially, the DFT calculation was not able to explain our findings, because it was providing some very different electronic structure with flatter states, and they were all located above the Fermi level. In this case, it was shown that one can improve the agreement by taking into account the self-energy correction. In this way, he can get very good agreement with the band structure. So not only after including this self-energy correction, it was found that ytterbium also have some, XCP ytterbium also have some topological properties which emerge after one takes into account this self-energy correction by Hubbard Hubbard correction. So in this way, the ARPAS and DFT were nicely collaborating and found also something which was not there before. That was the first evidence for a direct nodal line in lanthanum with metal. So then also there are some examples of other simple bond structure like graphene. For example, for the Fringe state and graphene, there is a very good agreement between the bond structure calculations and also graphene on low interacting substrate like graphene on silicon carbide. And you can find this Dirac very close to the Fermi level. And the only difference with the calculation might be just the energy shift of the bonds due to the doping. And differently in graphene that is grown on some interacting substrate, the ARPAS can provide the information whether there are strong interaction with the substrate. If in case you see the, for example, this Dirac that comes close to the Fermi surface, you can judge that the material is more freestanding-like. But when it is, for example, the nickel is intercalated below the graphene, you can see that the graphene is nearly destroyed. And so ARPAS can say that there is more interaction with the substrate. In the same way, it can work in the reversed way. So when the graphene is strongly interacted, one can intercalate the silver below the graphene level and restore the linear shape of the graphene and say that, okay, now the graphene is mostly freestanding. So ARPAS can probe also the degree of the interaction of the material with the substrate. Another example of the study of the two-dimensional material is the study of silicene. Silicene is also the analog of graphene that is built of silicene atom arranged in a honeycomb lattice. With a difference with graphene, these atoms are this sheet is slightly buckled, so it's expected to induce some particular properties in the graphene bond structure. In low buckled configuration, the graphene is expected to, or silicene is also expected to show a Dirac close to the Fermi level, very similar to that of graphene. And since silicene was grown on silver 111 surface, there was an early ARPAS report that they also observed something which was a linear band close to the Fermi level. Since they were expecting a linear band from the calculations, it was reported as evidence of the Dirac cone-like state in the silicene. But indeed, then if one analyzes carefully the band structure in two-dimensional, like about anisotropy, it can be seen that this band was not having the correct topology. It was not a cone. It was just a saddle-like point. That means you see maxima along one direction and minima along another direction. And indeed, the calculations that were taken into account the substrate were shown that there is a very strong interaction with the substrate. So the original Dirac cone is destroyed, and so there is no more Dirac cone. And also the states which are seen, they are mostly the silver states that they are modified by silicon. Okay, so just to be sure that not every linear band is necessarily a Dirac cone. And it always requires a 3D analysis. Okay, so shall I go fast?
Well, I mean, you have a few more minutes.
So okay, then I can skip to probably this part. I will tell about the importance of the topology of the photon energy dependent ARPAS that is provided by synchrotron. The band structure, as the previous lecture taught, is very sensitive to photon energy. In particular, you can see different features in a different manner. For example, this is a topological insulator bismuth selenide, and you can see that there is much more intensity on the surface state with respect to the bulk states. And varying the photon energy, you can choose mostly the feature which you want to see. It can be also very crucial. Since, for example, in this case, there are some selected photon energy where you can see the topological surface state, while at a different energy you do not see it. And initially it was claimed that there is no topological surface state in this type of antiferromagnetic topological insulator. And also the photon energy dependent ARPAS can provide the information on the bulk bands of the states that can also be converted to the wave vector of the electron inside the material. The relation is a bit more complicated. It also needs several assumptions, like for example, like the final states in the form of free electron-like states. Then from there, one can also relate the variation in the dispersion in the intensity of the states in their position with the bulk states that are shown by calculations. And okay, there are also, okay, I believe I do not have much time. Okay, there is also one of the most advances of the ARPAS that can allow us to measure the spin resolved band structure. It can be also done in not only for one spin direction, but also for all 3 dimensions. One can take the vectorial spin analysis. For example, it can also be done in the form of angle resolved photoemission together with the spin resolution can provide these bands. The time which is required to take this type of maps is due to the sensitivity of spin resolved ARPAS is much higher, like this might take several hours with respect that this might take several minutes. It's just this order of magnitude higher, the time which is needed. This can be done also for topological surface state. The spin resolved ARPAS can be also used to resolve between the individual bands that are closely lined. They're so close that even the band width is higher than the peak separation. Using the spin resolution, they can finally resolve also the features which are not possible to resolve otherwise. Okay, there are also the laser-based ARPAS can probe the non-occupied band structure and also can allow for studying of the dynamics of the states that are excited. There are also, I have to skip probably a bit faster, no, because we are running. Then there are also some extensions to ARPAS that can use some focusing elements and then allow to reduce the spot size on the samples to several microns. And this way, one can study an inhomogeneous sample and then can find very small pieces of the elements and study their band structure. One can also use the electrical gating for some layer materials. In this way, apply the electronic voltage to the electrical voltage to the sample, roughly speaking, and also move the Fermi levels of the material and access the non-occupied states. This is some very new experiments which were recently done also at the electrosynchrotron. And and the last part is that one can also use completely another type of electron spectroscopy, that instead of measuring the spectra, it can measure the inverse, it can take all the electrons from the surface, and they are all projected on the image plane. And so instead of spectra, you are getting this, directly you get these constant energy cuts. And then with this is called magneto microscope because they are not resolved in angle, but they are resolved in inverse angstrom space directly. In this structure can also be coupled to spin, but in this case, so far the spin is measured only along one spin quantization axis. In this way, you can also get directly the constant energy counters that are spin resolved. And you can take them as form as photon energy, and you can build all the 3-dimensional band structure of the element with spin resolution. And so I come to the conclusion. So photoemission spectroscopy is one of the most direct experimental methods to probe the electronic structure of solids, and there are a rich variety of light sources and detection systems. And the ARPAS is there are a lot of new developments in the field of ARPAS. Much new instrumentation is coming in the last years, and the possibilities of ARPAS are continuously growing. Thank you very much for your attention.
So thank you very much, Polina. I think there were very nice examples from which to start for the discussion. So let me just start with a comment for the example of silicene on silver was the example. And I think, I guess one of the points of this talk is that ARPAS is is a very powerful technique to get the mass structure and to directly connect with what we do. But there are a lot of technicalities, which Polina was discussing, the photon energy, the sensitivity to the surface, the substrate, etc. And so we have really to pay attention to, when we do a calculation, not to jump to the conclusion that we can directly describe what is measured experimentally. And I think the example of silicene is nice, because I'm sure there was some theoretician who was ready to say, yeah, this is exactly the band of silicene, I'm able to compute it and I get the same, but in the end it was the band of the substrate.
Yeah, so it was just, as far as I remember, it was depending also on the thickness of the slab one was using for the calculation. When one was using like a 5-layer slab, one was shown a linear band, but also these linear bands are coming from silver itself.
Exactly, so the point is that pay attention, not to just directly jump to the conclusion. Huh? Yeah, okay, so then we can start with the questions, maybe, yeah. And first of all, if there is someone in the audience. Okay. And then.
So I just want to know, please, can you please comment on this, the layer resolved measurement? How deep can you measure? So
sorry?
The layer resolved, yes, measurements of our.
So how deep you can go in the sample?
How deep we can go on the sample, it depends on the photon energy, basically. If we look, if I look on this this one. So basically you look, it depends on the photon energy. In this photon energy there are photoemission probes that can go like 2 nanometers, that means up to 10 atomic layers.
Okay.
Hello. I just want to ask about the part that ARPES plus spin that you introduced. Is it possible to find the lifetime of the this electron that just excited and going to the higher state?
I know that there is an example for also spin resolved, like these are, I just introduced these time resolved studies. I know that these can be also performed with spin resolution.
Okay.
The problem of these time resolved studies, it was in my experience that you normally you have very low resolution. So you have already low resolution when you study the time resolved structure, plus when you are adding the spin, you are normally decrease it by 100 of times, so you're increasing by 100 of times all the acquisition times. So these are some particular measurements. I have seen some of them in the literature, but it can be done, as far as I know.
Okay, thank you.
And then, Polina, in the static measurement, you can also inspect the line width to say something about the lifetime, no?
Ooh.
Oh.
Yeah, probably yes.
So,
that's not a lifetime.
yeah, okay, yeah.
Okay, we have 4 questions from the chat. Okay, can one say that there is band crossing if the observed band gap is of 1 to 10 millielectron volt?
Oh, it depends on the resolution of your system normally. So there are some dedicated beamlines that will study very high resolution. You have to go to very low temperature probably. You have to increase your resolution by several times. Probably with the laser-based techniques like here, you can effectively do this.
And the second question instead is, how can we choose the exact probing energy in order to photo-eject the electrons from the materials? I think the question is how you select the photon energy. On the basis of what?
Normally what you select in the photon energy is when you better see the features. So you can, when you have a tunable energy, you can just take several energies and select what you are interested in, where you have better contrast there to see. When you can have emission from the sample, you just need to have a photon energy that is higher than the work function. It's typically, I don't know, 4, 5, 6, 7 electron volt.
And there is actually a question interesting about the minima in the plot of the mean free path as a function of kinetic energy. Is wondering why there is a minimum at 100 eV.
Yeah, from 50 to 100 eV. Yeah, because, okay, I'm not ready to answer this question. I know that at lower energies, these electrons can penetrate deeply into the sample. That's what I know, but it was, I believe it is also not available for, the curve is not also is not available for the materials. Yeah, I believe the theoretician may answer better this question.
But I submitted, I knew the answer, but now I don't remember. So there is a double trend, so as you can see, but I don't remember the reason for that.
Can we detect electron phonon coupling by ARPAs?
Yes, basically we can. I'm not expert of that because our beamline is not some very high resolution. We do say a lot of a bit of everything. So I know that electron phonon coupling, for example, can be nicely seen here even in the copper 111 surface state when you use the laser-based ARPA. It has a very good beam stability and a very good energy resolution and so on. So you can see this kink. Sorry, the electron photon coupling can be seen that you do not see a straight band which comes directly to the Fermi surface. You can see there is this change in the band slope. And from there, one can estimate these different parameters that are related to the electron photon coupling.
Okay, the last question is how tricky is to prepare the samples for performing ARPAS measurements? Can we control the environment to avoid, for instance, oxidation at the surface?
Yeah, of course, that we say in our system we can do that because in our photoemission beamline we can go very high in the energy. We can, okay, here it's not written, but we can go up to 1000 of electron volts. That means we are covering binding core levels of the oxygen. So we can also follow, okay, like it was in this example, we can also see what happens to the oxygen. How it's difficult to prepare the sample, it depends also on the sample. Some sample, like a topology consolator, you can just bring into the vacuum, you cleave the surface and you can measure it. Sometimes you can spend several days just trying to prepare the surface and you are not getting it. It depends a lot.
Okay, so any more questions from the audience?
So may sound super stupid, but how do you separate the band structures of the interested material and the substrates of, like, for example, how do you post-process these things?
One can distinguish between the surface-related features and the bulk-related features by taking the photon energy dependence. If you have a synchrotron, then you can tune the light, and basically the surface-related features, like here, you see this, this cut, the surface-related feature, which is the surface state, they remain fixed. They do not change their position with the photon energy. While the bulk-derived feature, they normally change. It also is not always like this. For example, in the case of silicene, that feature which was reported for silicene as a Dirac, it was not changing with the photon energy. But because this is some particular silver state that stays there because the density of states is high there.
Okay, so thank you very much, Polina, again. I guess it's time for lunch. Everyone is ready to go to eat. And yeah, let's thank Polina.
You're welcome.
And okay, so now for lunch, we will...